Right. So yesterday, so we've finished up this Python 3.13 support. That's all published. So really good to have that out of the way. And so the next things to do over the next couple of sessions is basically just issue triage, or going through some of the issues that have been sitting around while I've been focused on that. So one of the ones which I wanted to look at is this report of speed regression. So the user here very helpfully provided a lot of initial analysis that should make it easy to pick up the work and see what's going on. So yeah, hopefully I can make a meaningful patch on this in the next couple of hours. And if not, then at least we'll understand a bit more about what's going on. So let me just do a little bit of stream setup. Yeah. Cool. Okay, make sure I've got the chat up. Stop chat. Okay. Yeah, cool. All right. So now, start. All right. Now I'll just drop a quick note. I thought I had that posted as me. Anyway, rather than an explosion. Cool. All right. So let's get started. Transition scene. Cool. All right. Am I in the right? I think, yeah, cool. What's this term? Good. Alright, so while that's installing, let's go back and actually work through this issue and think about what's going on. So, dear spaCy team, I recently upgraded from spaCy v3.3.1 to v3.7.5 and observed a significant slowdown on GPU when using the same model and input data. Upon investigating, the issue appears related to the introduction of spaCy curated transformers starting from v3.7.0. So spaCy curated transformers is our own wrapper of the transformers models. We wanted to have a library which gives essentially consolidated implementations. So the same layer. Different models will all access the same layer function underneath, as opposed to the more flat and duplicated implementation in transformers. This also gives us more control over things. The downside is apparently we've seen some performance regressions. So, all right. Okay, all of this looks correct. There's nothing surprising there. Now, I wouldn't be surprised if the nature of the issue is actually that when you process one text, that there's different overheads, and the expected performance scenario of running more texts through it. So actually, hang on, how many texts do we have here? So we go texts, and yeah, so this is only calling one text. So it could well be that we've just got overheads, and it's going to be difficult to fully prioritize the more major consideration is always going to be throughput when you're dealing with larger batches. So if we do have a trade-off to make around throughput and performance and latency on a single text, usually we're going to prefer the throughput. That said, we do want to care about this, and the difference here is stark enough that because I don't know what causes it, it's well worth looking into. Okay, so yeah. With non-WS tokens for, specifically it seems add whitespace tokens. So alloc2f, yeah. And then for each non-WS token, the tokens vector is copied with, yeah. In the text samples I have, the majority of tokens are not whitespace. So I think if this copy was done such that the entire vector is copied to new layer, and then whitespace tokens can get specifically zeroed out, which would result in less operations and speed up the inference. Yeah, okay, I can see that. Bottleneck. It looks like there's a bottleneck in byte. Okay. So yeah, first things first, let's get the script set up. Alright, so we can do the script production. Cool. Okay, so we'll pop back to the terminal. Good. Okay. And now. And every time I do this, it's always there's always some extra step that I forget to do when setting up the GPU. So hopefully we don't have too much trouble with it. I think it's mostly a matter of setting the environment variable for CUDA. While that's doing, I'll just open it. Terminal. Okay. No. Let's go. 1 second. Alright, yep, so it's downloading there. And here we can do, so yeah, I'm just typing in a different terminal while I wait for that to clone. I'm just setting up the clone of, waiting for that to install. I'm just setting up the clone of spaCy curated transformers. Yeah, there we are. Okay. So let's just transition back and look at the code here. So let's have a look at when this offending code was happening. Pattern used with non-WS tokens. This model wraps a sentence piece plus transformer chain and feeds the token without whitespace to the chain. Stub 0 representation for whitespace in the output. Okay. It does seem like you would want to do this the way that the user suggests, that we would want to invert the assignments. So we would start with a copy of what you had. So doc alignment WSN pieces hidden with. So yeah, but then the alignments are different. So for alignment in doc alignment. WS token adapter out. Okay, all right, let's get back to okay, so just making a temporary directory for this. Let's see. Okay. There we are. Yep. Let's try to remember which CUDA we've got. CuPy, CUDA, 12x. Invalid device. Okay. That's wrong. Okay, cool. All right, so that's times 1, and it's a cumulative time. So let's see reporting here. Alright, so let's input this datasets, then okay, now okay. Now, while that's doing, in a different window, I'll also start setting up an installation of what version did you compare against here? 3.3.1, spaCy 331. Okay. Equals 2.1. Okay. That's not so nice. Okay, so I might need to install Python 3.10, but because there's no wheel here for spaCy, but I'll give it a go. I'll see. I predict it'll end up failing at some point during the installation. Okay, so here we go. So indeed, the with non-WS tokens forward does take too long. Likewise, you'd hope to see from this the thing being dominated by matrix multiplications. But this is not what I immediately see. These are torch calls. Predict. So unfortunately, the fact that we've got all of these, there's a lot of CUDA compilation stuff, it really is going to make the benchmarking hard to compare. It's also not, is this a valid way to do things as well? Because are we going to end up getting tripped up by the fact that the GPU stuff's called asynchronously? So okay, let's take a look through this. So we go transform model forward, 368, 648. So we go model.layer 0. Okay. Yeah. Then that calls into with non-WS tokens. just check on the compilation here. No, okay. So let's see. In this other window, I'm just going to work on getting Python 3.10 set up and set up. Do I have pyenv? Let's see. Okay. Okay, let's see. So yeah, I'm just in another window installing Python 3.10. And that's necessary because I need to install this older version of spaCy, and there's no wheels for it on Python 3.12, which is the version that I'm mostly using. Okay, so alright, that should be installed happily. So yeah, I'm just looking at this and I'm sort of I'm just trying to think through the logic and what everything is. So, whitespace tokens. There's the non-whitespace tokens and a mapping from the non-whitespace token offsets to the number of whitespaces that preceded the token. For docking docs, yeah, okay, so token dot is space offsets is equals 1. It's an interesting way of doing that. Okay. Usually, I would have expected it to be a direct mapping of, like, index to index. So, what's the index of the token before and what's the index of the token in the other one? So, let's see. So we got token WS counts, and that's it, and then we produce, yeah, okay, so that's the tokens without the white spaces, and then we do the inverse. Modify the model outputs in place, blah, blah, blah. And then we add them back in. So yeah, this is this wrapper that you call around the model that expects to operate without the white space tokens, and then you remove them from those outputs and then recalculate afterwards. So let's see, what's our token alignment? WS piece offset of the token within the DOL without white space tokens. White space tokens have none as their offset since they are not represented in piece sequences without white space. So this is also important. There's a copy to NumPy here that can be so I'm tempted to do this the way that I would do it and compare. So test with white space tokens. Cool. Okay, so let's take a look at our sample dots with spaces. Okay. Test. So here we have this sort of thing, and in spaCy, this stuff becomes a token, but that token is something that the underlying model doesn't know what to do with. So what we do is we filter those things out, pass it to the inner model, get the predictions on those things, and then map that back. And this process of the mapping back and forth is what's taking time. Okay, so let's just dive in here. So let's see. We've got tokens, and then this is going to give us, if we're going to get array, and then we can say well, let's do this even simpler. We'll go box, and then array. And now we're going to undo. This callback will okay, so let's see, x x with white space, and then we need to say how does this work again? Curate transforms models with white space tokens forward. Okay. So yeah, we've got our X WS token adapter in T. Alright. Top pieces in T. Yeah, okay. So docs and IDs. Well, we'll just call this X. With white space, and then we're going to get no white space, and we're going to return white space. Okay, and then we're going to return no white space and undo. Okay, so oh wait, no, this is not correct. Okay, so we go no white space, and then we got with white space. Array, white space. Okay, so X with white space, and then we're going to return X no white space, and then here this is going to be, this is going to take Y no white space and return Y white space. Okay, so and then we might have, you know, NumPy so, and then we've got some, let's imagine we've got some inner model, so no white space equals tokens white space. Then we're going to do you know, and then we can go turn white space, we can do undo. So now the reason I'm I do this in this callback is this out of context doesn't care what intermediate stuff is needed to reverse the mapping. That's an implementation detail. So if we just return a callback, we can store that stuff in scope and change that flexibly. So first thing is let's see what white space map do we need? So how are we doing this white space count? We've got this filter tokens. Why don't we check whether something's... Yeah, okay, docs, okay. All right, so my first thought is we go equals docs. Then we go so now let's start doing some typing just to so let's say that this is a list of ND arrays. So what is TOC pieces in T? Where are we? Types, surely. Under models types. Oh yeah, okay. So WS token adapter in T. WS token adapter out T is a transformer model output. And what's a transformer model output? Okay, so it's the starter class. It's TRF output T. Okay, so it's a first T array. Alright, cool. So yeah, it's going to be some sort of ND array or something like that. Cool. Alright, so we can say we're going to be taking a list doc. Of a list ND array. So for simplicity, we'll actually just make this one block. Okay, so we've got this. And then we're going to have a tuple of this and callable that you call with ND array. Cool. Good. Alright, sweet. So let's see. What would I do for the alignments? would say is alignment and so I guess we probably want this bidirectional, but let's see, we'll start with the indices into so we go I here. That's actually all that we need for this version. So that means that if you want to index into the originals, you can just do this with this. And that will select the ones which you need. So then the inverse. Actually don't need this. And then we go inverse double append, then align. So that's not quite right. Like we can do it this way and then zero them afterwards. So yeah, inverse, and then the white space positions would be so this would be this would be okay. Okay, so now we go so let's see. Oops. So, yeah. So let's see. The first one indexes into. So we go mode. So it's WS to no, no to WS, and space. Nice. Alright, so space array, then down to WS. Then, so in order to get the X no white space, we say we go X white space and WS to no. Okay. And then we have our undo function. So this is going to be in the array. Okay. And now we'll go WS equals no white space with no to WS times white space map. And then we go 1 WS times equals WS map. Okay. No to WS 0. hang on, XWS equals, no, this, yeah, okay. So, WS to no, we will go, let's see, the first one is 0, then the second one is 1, we'll go 2, we'll go 4, then 6, right, then we go, hello, no, 2WS, this would be, okay, 0 maps to 0, 1 maps to 1, 2 maps to 2, 3, again it doesn't actually matter what we map to here, but we map to 2 there, then next one we need to map to this guy, so we go 3 in that one, and then 4 in the so like 3, and then where do we have the missing thing? So yeah. Two, 7. Okay, so that's the inputs. Then we need, yeah, that's good. So then this maps to that one, that maps to that one, maps to that one. This one, it doesn't matter what it maps to. And then this maps to here. Then doesn't matter what this one maps to. And then 1, 2, 3, 4, 5. Okay. Then we go to this map. We go 1, 1, 1, 0, 1, 0, 1. Okay, so then we remove white space. We go X I for in WS to no, then we'll restore white space, Y I for I in no to WS. Okay, alright, so that all makes sense. question is whether this approach should be, will actually be faster. I think it will, because it's one index operation per doc. And I don't see how this can be slowed. It can be slower to create the map. So it's one index operation and then a multiplication. Whereas, what do we do here? Yeah, see, this more alignment in dock alignment, new layer, alignment.ws piece offset. So this is, yeah, it's aligning per chunk, which I just, and we get our lengths. So how do we end up with this ragged array here? Is this actually even what we need? Seems weird. Why do we end up with these raggeds? What are we actually storing here? Let's read some docs. Oh, have I been... don't tell me I wasn't on the code this whole time. That's frustrating. Alright, well, sorry about that. So yeah, basically this is what I was doing. This is what I was muttering to myself about. Yeah. Let's see. Alright. So yeah, I've been going over this implementation of the spaCy curated transformers and making my own version of it with my own logic, so that I can see what's going on. The thing is, I'm not sure that the output that I'm actually getting here will be it looks like that's not going to be the output that the code here expects. The code here expects a ragged array where the lengths are the lengths, the number of tokens that each token is mapped to. I'm not sure. All right, let's flip back like we wanted to do and actually look at the docs for this. So where are we? spaCy curated transformers. All right, there's the PR here. What's that? Oh, 2 tenses. Oh, okay, that's something to look look at later. Okay, so we go here, pipeline transformer. Okay, so we need to assign to this doc.trf data. That's the same as we have in explosion, spaCy, transformers. Okay, so embeddings, transformers, and okay. TRF data. Let's return tensors that refer to a whole padded batch of documents. These tensors are wrapped into the full transformer batch object. The full transformer batch then splits out the per document data, which is handled by this class. Instances of this class are typically assigned to the... Okay. A slice of the tokens data produced by the tokenizer. Yeah, alright. Model output from the transformer model. Okay. Alignment from the docs tokenization to the word pieces. This is a ragged array where the aligned lengths indicates the number of word piece tokens the token I aligns against. The actual indices are provided at align I data xd. The width of the last hidden layer. Okay. And output objects for transform model. Okay. So let's go back to the code. Wrapper for PyTorch transformer output consumed by downstream non-PyTorch components. Also access the accumulator for outputs of subsequent models in the transformer pipeline. Non-padded, unstacked versions of the outputs. The outer list tracks docs and the inner list tracks the embedding plus hidden layer outputs of each doc. The innermost element is a floats 2D and returned by the PyTorch wrapper transform model, which is subsequently converted to ragged by the models that follow. Each ragged element corresponds to a layer in the original transformer output containing representations of piece identifiers. Okay. So what we ultimately want to do is we want so yeah, okay, this is fine. We've got this stuff, which is the in the word piece space, but then we also need the number of tokens, the number of word pieces that each token is aligned against. So here we've got our alignments. Okay, create alignments. An alignment between white space and non-white space sequences. Okay. So we won't worry about that part yet. Basically, once we've got this single array, we then need to make it into a form that you can easily get. Like this is an array of the word piece outputs, and then we want to be able to index into it and say like, okay, I'm the 12th token. What are the word pieces that represent my representation? And that's something which, okay, fine, we can do. All right. Yeah. So how do we actually find the word piecings and stuff? What are we actually passing in here? Let's go take a look one step up. So if we go to spaCy curator transformers and we're looking at pipeline components. So let's see, what do we do here? All right, in our predict thing. So we go, yep, there's the outputs, set model all layer outputs. Okay. So we need to go in one layer deeper into the model. Models, let's see. Architectures. Build transformer or listener wrapper. Okay. Build transform model V1. Cool. Okay. Piece encoder with spans. And then remove BOS, EOS. Alright, what happens with spans? Structured model can be used to convert a list of ragged piece identifiers to strided spans and vice versa. How can this be right? That's so weird. I guess it's this. Okay, well, anyway. So my question is, how do we end up knowing the length of the word pieces? Like, where does that bit happen? Where do we say with non-white-space tokens forward? So inner model of layer 0 tokens WS counts. It doesn't seem like we should have that at all here. So let's see. Talk to pieces into inner. tokenization types. Okay, so talk to pieces in T. Right, so there we have, so here this is actually a list of token sequence T. Now what's a token sequence? Well, that really is filter out whitespace tokens, returns the non-whitespace tokens and a mapping. So we're actually just returning the tokens. We're not even doing any anything else. So then that, yeah, so there we get the tokens. So we go create alignments. We've got WS token out T. Doc alignment. Where do we get the doc alignment? And pieces. Where do we get the pieces length? Pieces length, model of doc output 0 dot lengths. Okay. So where have we got this output? Okay, create alignments. Model liner WS. Okay, so we do the filter tokens. Talk pieces into list token sequence. Okay. Doc tokens. Right, okay, it's even easier. We don't have to deal with the arrays at all. So we go, yeah, so we've got filter tokens. So let's see. Doc, we can go tuple token and then this will be callable from list token. Actually, so this is, so here we do have these arrays that we have to map back and forth. Okay, that's fine. So okay, so here we go, XWS. So, then we go X, no, WS, so we go yeah, so we can do it that way, but so it's for WS2. Okay. Yeah, and then okay, and then what I'll do is we're receiving this output thing. Yeah, so that's fine. Okay, that's fine. Undo. So now this token and then our callable. This is wrong. Yeah, cool. All right, so I'm pretty sure this will improve things. It's pretty much in line with what the commenter was suggesting. So let's just go back here. Alright, so here's the issue. And indeed we say, I'm far from an expert here, but how to speed up transformer inference. Curiously long time has been in the following calls. Add white space tokens. It seems like a lot of time spent allocating new vectors here. For each non-WS token, the token's vector is copied. Examples like, yeah, such that the entire vector is copied and then white space tokens get specifically zeroed out, which would result in less operations and speed up the inference. Yeah, I mean, this makes sense. Yeah. Yeah, that looks extremely reasonable as well. Okay, so all right. I'll take a break for some food and sort of step away and think about this some more. But I think this is a good plan. Basically, I'll replace this function and then we can see whether it's made it faster. And then we can also take another look at the benchmarking here. Cool. All right. So yeah, I'll just transition this away. Okay. Okay, yeah. So yeah, I'll sort of fade this to black and well, I guess I could just pause the stream. Yeah, I'll just pause the stream. Okay. All right, so I'll be back in a bit, and hopefully we can get something running.